My name is Prashant Kumar Pandey. Today we are going to cover the topic properties of solid materials. In that, we will be covering elastic and plastic materials, stress and its type, strain and its type, stress versus strain diagram, and if time allows us, we will also know about the Hooke's law and what are its applications. Let us start with the elastic and plastic materials. What are the elastic materials? Let us suppose we are having some object like this, and we have fixed this at 1, and we are applying some force, external force, in order to deform it. What actually happens, it will extend up to some limit. Okay, and there will be some restoring forces that will be developed inside it. So what actually happens, when we remove the load, some of the times the material regains its shape, and sometimes the material will not regain its shape. It will remain as it is. So when the material is regaining its shape, it will be said as elastic material. And when material is not able to regain its shape, it is known as plastic material. So we will be dealing with elastic material and plastic material. The example of elastic materials are steel, and the example of plastic material we can say clay. Okay. Steel is something like when we are applying some forces, it will have some deformation, and once we are removing the stresses, it will again regain its shape. So we can say it as steel. And on a clay, if we said we are applying some forces, it will deform and it will remain in its shape whatever it has been. Okay, let us study about stress and its type. Stress is something that internal resistive forces that have been developed against applied external loading. So stress can be defined in different types. We can say normal stresses. We can say shear stress. We can say volumetric stress. Normal stresses are further divided into two types. That will be compressive stresses, and that some other will be tensile stress. Let us suppose we are having some object like this. Okay, 3D objects. We are applying the forces in this direction. This body is having area, a cross section area. We are applying some force here also, in this direction also. So what will actually happen? This body will elongate, and the means area will decrease. So stress can be given as force that will be resistive forces inside, that will be produced inside the body, upon divided by area. And again, when we are applying the forces in similar way, and this very time, what we are actually doing, we are trying to compress this body. Internal resistive forces, we are applying force in this direction. What will happen? Body will compress. Here we are elongating the body. Here compression of body will take place. Normal area normal to this, compression of body will take place. Okay, what we can say, that this will be a tensile stress. Tensile means elongation. We are trying to pull the object from both the sides in this direction. What we are doing, we are actually trying to compress this thing. So the size will decrease, here size will increase. So we can say that this will be a this is compressive stress. This is the example of compressive stress. And this is example of tensile stress. Okay, now we can see this, what are the shear stresses of. Let's suppose there is a body which is fixed at the ground. There's a body, we have fixed this at very ground. What we are actually trying to do, we are applying the load over here, F. So what will happen over here? The body is fixed at the bottom, so there will be a deformation in the body, in upper portion of a body, and it will be like this. We can see this in this form. The body will be deformed and the new shape will be like this. Okay, so the deformation, this is x. If we are supposing this is x and this is h, so deformation is taking, this will be very small. This will be not about, this will be about 1 2 degree 3 degree, not more than that. Sometimes it may reach to up to 5 or 7 degree, but not it will not be like 30 or 40 or 60 degrees. It will be very small values, and this deformation can be given by x by h. So when we are applying this type of a load over the body is getting this means disturbed, means we are deforming the body actually. So these type of stresses, when we are applying over a body by fixing it, this type of stress is known as shear stress. Shear stress. Okay. Let us see about volumetric stress. What the volumetric stress is? Let us suppose there is some body. There is some body like this, kept like this. Okay, and all from all the directions pressures being applied over this. Okay, when we are applying with different pressures, means atmospheric pressure is already applied, there will be some excess pressure other than atmospheric pressure. Okay, so what will actually happen? Where it will be like this. So what will happen? The body will deform in this way. And this deformation of a body is because of the excess pressure, excess than atmospheric pressure. It is not atmospheric pressure. We are applying some extra excess pressure than atmospheric pressure, then this deformation will take place. And this type of stresses, when bodies means when this type of stresses are applied over a body, there will be a change in entire volume of it, and that change will be delta v. There might be some change, means other things, but we are not taking. Let us take about different types of strains. Each time, each stresses will have its own strain. Means we can have normal strain, we can have normal shear strain, and we can have volumetric strain. Strain is actually something like deformation to that of original length or area or a volume. Deformation actually, if let us suppose we are having this object. Okay, we have applied forces over it, and the body get deformed by this length. Okay, initial length was like this, we are having new length, this will be L plus delta L. Okay, this delta L is increment in the length because of applied forces F. Okay, so strain will be equals to delta L upon L, and this strain is known as normal strain. Okay, when we will be talking about the shear strain, similar example we can take. We have taken an object which is fixed at a ground, we are applying a forces over here, and it is getting deformed in this shape. Okay, so this deformation delta, what we are getting, or theta x, and let us suppose the height of our object is, so this theta will be given by x by h, and this is known as shear strain. Similarly, if we will talk about the body, another volumetric strain, we can say that, let us suppose similar example what we have taken in the case of shear volumetric stress. So because of external pressure what we are applying, actually there will be a deformation, entire volume will change. Initially this was the volume, now we are getting a change in a volume v dash, and let us suppose this v minus v dash, what we are getting is actually delta v. So the volumetric strain will be strain equals to delta v by v, but what we are getting a negative decrement in a volume, so we have to show negative. Okay, now let us study about this stress and strain graph. Okay, here we can say that from starting, if we say it's O, from O to A, we are saying that there is a linear increment in the graph. This is a general graph for any material, where each material having its own stress versus strain behavior. We have taken just for steel. Okay, let us see what we are doing from O to A. There is a linear behavior. Linear behavior refers that stress and stresses are directly proportional to strain. Okay, here as the stress will increase, the strain will correspondingly increase. So this area is also known as we can say that proportionality limit. And we can say that this O to A region is something which is known as Hooke's law. It's also described. It was described by Hooke. Okay, in Hooke's law, stress is directly proportional to strain. When we talk about stress, it will be equals to something y into strain, and this y is modulus of elasticity. Sorry. Or we can say that we also know this by Young's modulus. Okay, from A to B region, what we are actually saying that there is increment in length, but it is not linear. So this also comes within a elastic limit, but the behavior is changed from linear to some curve, or we can say that something different behavior than linearity. So it is also under elastic limit, but we are not getting a linearity in that. Okay, and once we are moving after B. Okay, I have mentioned these things because these are important. We need to know each and every point. From B to C, what we are actually saying, the material is entering in a plastic behavior, because after the point B, if we are applying the stress, then material or a substance will go under permanent deformation. What this is what has been represented by BC. Here we will be getting a permanent deformation. Okay, and from again this point C is known as lower yield point. Okay, again when even we if we are applying the load, then we can see this type of behavior will be seen. And what this is happening because strain hardening or molecules are again trying to get attached to each other. That is why this is getting curve is means even after increasing the stress, we are getting a increase in strain also. So from C to D, there is a strain hardening. That is why the curve is increasing. And after this point D, we can say that this point D is ultimate point, ultimate stress point. From D to E again, there will be decrement of even after means even we are decreasing the stress. Okay, then also the strain is even we are decreasing the stress, then also strain is increasing, and we will reach at a fracture point. This is known as fracture. Here material will completely fail. So we can say that from O to A and A to B, elastic behavior, and from B to C, C to D, there will be, and even we can say that D to E also there will be a plastic behavior. Okay, and at E we will be getting a fracture, means material will completely deform. Thank you guys, that's all for this class. We will meet again.